Thank you very much for being here. Thanks for taking this time, and I will, after the day is long, so I will try to captivate your attention. You will not see fancy slides. I'm an engineer, I'm minimalist, so the emphasis will be more on content, and hopefully I will try, I will do my best to carry you through a journey about this, let's see if it works, yes it does, through some concepts, edge AI, computer vision, industrial application, that we have debated a lot today, and also in general there is a lot of debate about it, and though sometimes it's hard to catch value out of it. So I'm not here to try to sell anything. The point for me is to deliver you a value, probably leaving to you some open questions, and hopefully also giving you some insights about some challenges that are in this field. Just a few words about the company I represent. It's based in Modena. We have been operating for almost 15 years. We are a tech company with strong emphasis on vision and data analysis in general. And one of the main points of the vision is the effort and the ability that we developed along the years to go from ideas to prototyping, analysis, prototyping, and bringing these prototypes to deployment, so full deployment for creating industrial value. And we are agnostic to the industry. Another slides about our experience. These are the suppliers, the devices produced by these suppliers that we have used across the years to take computer vision and AI in general and bring it at the edge. So we have a quite broad experience, and through this experience we learn some lessons. Just a little disclaimer, there are here suppliers. It's not our point to raise one and lower another, absolutely. So this is the last slide. I will mention one supplier or the other, because the point is not one or the other. It's to understand the figure out of the technology and out of the challenges. Okay, so there is a bit of confusion, and also in this morning in a few conversations I see this confusion is even present among the people here about what is edge and embedded devices. And recently, to an important event about computer vision, I heard about calling this as an edge device. So I'm not here to say what's the right word to call this or that. The point is that for this talk, I'm going to focus on those. That kind of devices that have some features, and specifically on those I will stay focused on computer vision, that is part of our DNA, and on those kind of devices there are two main classes, microprocessors and microcontrollers. Our emphasis is more on microprocessor than microcontrollers, though even though we worked also on projects with microcontrollers, but they are two different families. So after all, embedded platforms have some features, specs. We could spend a lot of time debating what is exactly an embedded platform. We could say it's an industrial grade system that has very nice property, low cost, low size, low power consumption. So this is a provoking statement. If these are the features, who would be so stupid to continue using systems that are not embedded? If they cost more, they consume more, if they are bigger. Why? Let's make it very clear, of course, that there is something crucial that is missing out of this. And yet, those people that are not using embedded system are not stupid. There is a reason. And this is the reason, that there is a non-negligible design complexity that must be properly addressed to be successful in bringing embedded platforms into industrial applications. And this complexity touches several aspects. And of course, there is a lot of emphasis on AI. Of course, I think I lost, let's say, okay, on AI. But that's not only about AI. There is a lot of other things to pay attention to be successful in an industrial application that contains AI. And if you don't pay attention to the whole picture, you will fail, even if you have the best AI ever. All these things sounds trivial, sounds obvious, but believe me, they are not so obvious. And I find a recurring situation where there are underestimation of these simple and basic aspects. Of course, if there is a complexity, there is a cost behind complexity, and we believe that OEMs or ODMs are those business entities that can manage the complexity and can take the opportunity, making it heavier than the complexity of this design. This is quite hard for system integrators, or even worse for end users. So probably what we are going to talk about is really relevant if you are an OEM here or ODM. Okay, so I will go through the 4 pieces of the puzzle very quick, and for each of them I will just give spot insight and not complete overview about it, because they are too complex. So about sensor, I just want to talk about a couple of things that I saw that often creating problems in projects, in vision. The first one is the camera connectivity. I listed here a few types of camera connectivities that are all possible and all make sense for an edge device in a computer vision system. And all of them have different features. And I listed here 4 crucial important features where all of these camera connectivity formats should be evaluated. And I tried also to give some value, like good or not good or medium. Don't take this as undisputable evaluation of these features. But it's just to let you understand that we have been talking about today a lot about MIPI, CSI, but you shouldn't consider MIPI if you have to go through a distance of 50 centimeters. It's too long for MIPI. Or you shouldn't, for example, consider a TCP IP camera that carries compressed video data if you are looking for low latency. I mean, this, again, sounds trivial if you know them. Just a little understanding about a few of these. MIPI and GMSL are extremely relevant for embedded platforms. They deliver very high bandwidth and very, very low latency. But they shouldn't be taken in consideration if you are looking for a plug-and-play sensor, unless you have the luck to find the specific sensor that you like, supported by the hardware, the computing hardware that you are using. On the contrary, USB 2 and 3 and TCP/IP are extremely easy to use, I would say very friendly from the point of view of the use, but they have limited bandwidth, so they compress data very often. And last but not least, some machine vision standards like, let's see, I will stop using the pointer because it's very unpleasant, the flavor of it. These standards are proprietary. They introduce royalty costs. So the cost of this kind of sensor probably will not be as low as you need if you make a lot of volumes. Another topic that I think is relevant is the compression. Just to go to the earlier slide, remember the two central columns, USB 2 and 3 and TCP/IP, often introduce compression. And there is a sense that compression is always evil. That's not true. By the way, when we spoke today about generative AI, LLM, multimodal actually models, they all behave very, very well on video data that has compression artifacts. No problem at all. So compression is not evil by definition. Of course, if you have to tackle situation where you need pixel level accuracy, you cannot handle compression artifacts. But if that's not the case, you should seriously consider sensors that also convey data through compression. Because you lower the bandwidth to manage. You see here an example. It's an array of cameras, all connected to the same edge device. And this is doable only because the cameras carry compressed video data. Otherwise, if they were carrying raw data, the bandwidth would be so high that it would be unbearable by the edge device. Of course, if you have compressed data, you will need to decompress it, and that's a different story. You will need to use hardware decoders to avoid having a load on the CPU. A few words about early vision. Early vision means extracting intermediate features out of video data. And it's a bit old-fashioned today because AI is very greedy and has this approach that it takes everything, takes the video data, and delivers directly the result. So there is a sort of sense that early vision is for stuff that belongs to the past. I claim that this is not really true. Maybe in perspective it will be like that, but currently early vision still delivers a value. I have here three typical early vision tasks that still deliver a lot of value. And I'm not saying that you need to compute this necessarily with traditional techniques, even though you can. Optical flow or stereo matching or image warping for bird eye view, for example. You can do it. You can do all of this with traditional techniques or AI, but this can be a real help for the processing step that follow. And just two messages. This kind of processing can be very burdening on the calculation. I wrote here, though, what you can do through proper hardware acceleration. So you see some rule of thumb, computation load on CPU. Let's see. And you see how heavy it is to compute it on CPU of an ARM. And you see what you can achieve. Take these numbers with a pinch of salt, but you understand that you can strongly accelerate this kind of features extraction. And another message I would like to give you is through a project that I think conveys the idea I want to give, is this project where we had to compute the level of doneness of the cooking of food through, and we started tackling it with just optical cameras. And we delivered the algorithm to the edge. The performance was not fast enough for the target. So what we did was to add as input to the network, together with the RGB, also the dynamic of the scene through optical flow. And this was basically helping so much the network because it simplified the task itself, because the dynamicity brings a lot of value related to the task that allowed us to speed up the computing and reduce also the training set size. And this made a difference for the specific project. Okay, so just a word about AI. It was mentioned already. transformer. If we talk about edge AI, now means to address the topic of the transformer. Transformer is the basic architecture at the center of the transformation over AI that we see, but they are very demanding. They are very demanding, not only from a computation point of view. It would be an error to think only about computation, but it was said very clearly this morning as well, but it's about memory. And we are on the edge of a change, because there is a past generation of AI accelerator that somehow tackles transformer, somehow solves them, but it's not really brilliant. And some of the accelerators that are currently on the market do not even cover transformer. And there is a new generation coming, like the ones we saw this morning, mentioned by Halo and by NXP, that can properly solve compute transformers at the edge through massive DRAM, actually. That's the point. But is it all about transformers? Transformer deliver value when there are, according to our experience, one of these 3 points: extremely complex semantic to be extracted, or multimodality, or you need to do generative generation of content. And for example, you see here on the right the project where we used the transformer at the edge. By the way, it's our desk behind this door, so please visit us to see it running live. But if that's not the case, convolutional neural networks still convey a lot of value and can open, still today, great opportunities. It would be an error to put CNNs at the side just because today there is Gen AI. I believe that's my point. We can have a debate about it, but at least I'm talking about the current situation of technology. AI accelerators for CNNs today are mature. Software stack is mature. And from the hardware point of view of the acceleration, there is a wide spectrum from very powerful accelerator, external or on chip. You can compute CNNs on the CPUs only by exploiting properly Neon, or even, as we saw this morning, you can compute CNN acceleration on microcontrollers. You see, this is a camera with an AI accelerator on microcontroller. You understand? I mean, there are opportunities behind all these things. Just a few words about the platform. I sketched here some elements that sometimes get considered only in a very late stage of the design of the system, and sometimes considering them so late creates problem. I don't have the time, of course, to talk about all of this. I just want to give you a couple of insights about the first 2 ones, GPU and video encoding. About GPU, we have down in our table this application that creates virtual try-on for eyeglasses. And you will see there that there is 3D rendering, live 3D rendering, and you cannot do that on CPU. But you don't need necessarily to do 3D rendering live for requiring a CPU. Even if you want to do fancy UI graphic for your users, then you probably need a CPU because the GPU, because the CPU could be completely jammed by those calculations. The other point, and this is the very last thing, is video encoding. What you see here is an application we developed, but the graphics that you see are not computed at the edge. They are computed client-side in a selective manner. What does this mean? It means that the video gets compressed through the hardware encoder, and on the stream, we also insert the metadata, so that when the data is received by the clients, the client can selectively decide what to do with the metadata to extract statistics or do actuation, or create their own graphics live, client-side. But you need to carry the metadata together with the encoded video stream. Probably you don't think about this thing when you design the application, but it's proper to do that on time before the design gets too advanced in the timeline. Okay, so I stayed in the time. This is it.
Thank you, Giovanni.
Thank you very much.